Thank you, Tiffany. Mohsen, hopefully bring up the first slide. Kia ora koutou, my name is Nick Craddock-Henry, and I'm with Manaaki Whenua Land Care Research. And thank you to the first of a series of webinars looking at earthquake resilience in the primary sector. This webinar today sort of presents the first in terms of project outputs, looking at insights, evidence, and experience, particularly from the wine industry, with implications for other primary sectors. The project was funded by MPI, as I'll sort of discuss in a moment, and involved myself, as well as colleagues from Lincoln University, New Zealand wine growers, and the University of Auckland. We also work quite closely with a range of stakeholders from across the wine industry, including civil defense, Port of Nelson, and both small and large producers. Next slide, please. So nearly 5 years ago, the Kaikōura Marlborough Hurunui earthquake occurred just after midnight. The 7.8 magnitude earthquake resulted in over 25,000 co-seismic landslides, 21 faults ruptured, and resulted in significant surface faulting across the northern half of the South Island, resulting in significant road, rail, and port disruption. Next. For Marlborough region, this was the second large event in less than 5 years. In 2013, the Seddon Lake Grasmere earthquake occurred, which was about 6.5, and it came sort of less than 6 years after the 2010-11 Canterbury earthquake sequence. The shaking was significant enough not to cause damage to masonry buildings, many of which had been reinforced. But as you can see from the slides, and as Mohsen will discuss this afternoon, it did have a significant impact on winery infrastructure, as well as resulting in damage to surfaces, trellises, and vines were disrupted as well. For the wine industry, the earthquake came at a critical time as well. The 2016 vintage was in tanks, and it was awaiting distribution. So there was a significant volume of wine held on premises and in bottling factories when the earthquake occurred. Next. So with funding from MPI, we were successful in starting a project enhancing earthquake resilience in the wine industry, which was funded through MPI's Primary Industries Earthquake Recovery Fund, which was initiated soon after the earthquake. The overall aim of the project, which, as I say, was a collaboration between Manaaki Whenua, New Zealand wine growers, Lincoln and Auckland universities, was to really look at sort of key vulnerabilities and identify sort of resilience interventions throughout the value chain. So the overall aim was to look from the vineyard through to operations and market and understand how the interaction and feedback between impacts and implications had consequences for resilience, future preparedness, and so on. The project has run for about 3 years, and then we were delayed with COVID in terms of running the actual extension and outreach. And so this sort of portion of these webinars, as well as some fact sheets and vineyard tours coming up in the next couple of months, are really part of a way to extend to extend the knowledge that we learned, to continue to build on the networks, and to produce outputs that are actually useful, usable, and used for the industry. Next. So the project had 3 research aims. The first was to really document the structural impacts and the wine industry response. Second was to understand the interactions between the sort of social and ecological systems, so the markets, human behavior, decision-making, distribution, and use that information to explore new and appropriate initiatives. And finally, to initiate and enhance knowledge sharing to ensure that these lessons and experiences are shared with the rest of the wine industry. As Mohsen will point out, Marlborough is not unique in that many of New Zealand wine regions are actually located on significantly seismically active areas. While they may not have experienced earthquakes in the recent past, many of them, such as Hawke's Bay, have experienced them in the last century, and others are likely to experience them at some point in the future. So how how the lessons and experiences from Marlborough can be transferred elsewhere, both in terms of engineering solutions as well as how to manage market-related risks, is a key objective. Next. And so from our perspective, where we're coming from is really kind of this applied resilience science. Next. And when we talk about resilience, we really kind of mean the ability to adapt. How can systems adapt? How can they reorganize? And how can we learn so that we don't continue to make the same mistakes, or when there is an earthquake or there is a damaging event, simply build back or revert back to pre-existing ways of doing things, in a sense, locking in vulnerabilities or patterns rather than actually transforming or changing the system. Next. And so what we are really interested in is this ability to increase capability and capacity to buffer against shocks and stresses and to avoid critical tipping points or thresholds that may shift systems into undesirable states. And this is particularly important not only for the wine industry, but for other primary industries as they face the combined impacts of earthquakes, climate change, market-related shocks. We've seen recently COVID, of course, having a significant impact on the wine industry. And with primary industries making up a big portion of New Zealand's economy, ensuring and enhancing the resilience of these industries is vital to our long-term future. Next. And so over the next couple of months, we're presenting a series of webinars, the first of which is today, looking at seismic resilience of wine tanks and catwalks. The second one in November, we'll be reflecting on workforce resilience. The wine industry learned some significant lessons from the earthquakes and have made changes to the way they manage people. And many of those things came into play when they were needing to manage COVID response. And so we have a webinar planned, joining producers and other industry and community representatives to discuss some of those changes and how those lessons have been applied, not only in New Zealand, but some of them have been taken up internationally as well. And finally, we'll be looking at resilience in the wine supply chain. So again, there were significant impacts for supply chain and distribution following the immediate aftermath of the earthquake. And how can we mitigate some of those risks going forward? And what are the lessons and the similarities between the 2016 earthquake disruption and the ongoing pandemic? And how can some of those lessons be applied, and what else can be done in the future? So do please join us. We'll be announcing those in the coming weeks and make those links available as well. And so without further ado, I'll now pass over to Mohsen, who will discuss seismic resilience of wine tanks and catwalks.
Everyone, thank you for attending the webinar. My name is Mohsen Yazdanianm. I'm a fourth-year PhD student in the University of Auckland. And over the past 4 years, I have been researching on seismic resilience of wine tanks and catwalks. As Nick explained, a research program was established between the University of Auckland, LINKOnline, and Lanka Research Center, and also we had some other, there were some other consultants that also help us. Today I'm going to talk about the engineering part of this research, and I will cover the key learnings from the past earthquakes in New Zealand, and I will discuss about the remedial options that was recommended or followed for flat-based and legged tanks, as well as a probability of earthquake damage to the wine storage tanks. And finally, I will talk about a full-scale shaking table test for a 22 kiloliter legged tank. Our case study region was Marlborough, and as you may know, it's a very important region in terms of wine production, and almost 70% of wine in New Zealand is produced in this area. And over the past 10 years, there has been several significant earthquakes impacted Marlborough region, 2 in 2013 and 1 in 2016 Kaikōura earthquake with a magnitude of 7.8. And also based on the New Zealand seismic map, the Marlborough region is located in a high seismic area. There are 4 structural elements in a winery. We have buildings, and their functionality could be different from warehouses to the restaurants. We have catwalks. We have 2 types of catwalks, self-supported and tank-supported catwalks. And their main purpose is to provide access to the top part of the tank, and they are lightweight steel structures. We have also 2 types of racking system. The new generation, which showed performing well following our observations after the earthquake, and the old generation, which performed poorly. And we have wine tanks. Wine tanks are slender stainless steel structures with a very thin walled tank wall. And the main difference between the wine tanks and other liquid storage tanks is that they are slender. We have 2 types of wine tanks, flat base tanks and legged tanks. Let's have a look on a typical flat base tank. Normally, flat base tanks are composed of a turret at the top of the tank, top cone or roof, tank barrel or tank wall. There are normally several openings for access on tanks, and some of these access openings are only for pipes. And we have anchorage system, but there are different type of anchorage system, and I will later explain about the performance during the earthquakes. And we have concrete slab sitting below the tank. For the case of a legged tank, we have all those elements except legs. So the tank structure is sitting on leg, and they can be either anchored or unanchored to the concrete slab. Following the 2016 Kaikōura earthquake, we teamed up with structural engineers, and we inspected several wineries, and we held several workshops, and all in all, we collected the largest damage database for the wine storage tanks in the world, which is basically composed of 2 damage data sets, and today I'm only talking about the largest damage data set that we have. Our damage data set was covering both flat-based and legged tanks, and also covering data from 2013 earthquakes and 2016 earthquakes. So let's see an analysis of this damage data. This is a very high-level overall damage data. We have analyzed all data in detail, but because of the time, I will just give an overall percentage. For the case of flat-based tanks, in 2013 earthquakes, we noted that 73% of our tanks in the tanks in our inventory sustained damage, while this damage percentage reduced to 69% in 2016 Kaikōura earthquake. And although this earthquake had a larger magnitude compared with 2013 earthquakes, but still the damage percentage reduced, which could be because of the fact that some resilience measures were undertaken following the 2013 earthquakes, and some lessons learned from that earthquake, and that shows a good point that possibly because of the lessons learned from 2013 and 2016 earthquakes, now the wineries may have more resilience. We also analyzed the percentage of damage for different capacity range. On the horizontal line, we have capacity ranges, and we have damage percentage for each capacity group. Surprisingly, we can see that tanks with capacity range of 20 to 40 kiloliter sustained the largest damage in 2016 Kaikōura earthquake. And it was interesting to see that some largest wine tank sustained less damage compared with a smaller tank. We also analyzed damage percentage to different sections of the tank. And based on our damage data from 2013 and 2016 earthquakes, we can see that damage percentage to anchors reduced from 47% in 2013 to 23% in 2016. And that is because of the fact that we noticed a lot of several wineries actually implemented some and used some novel anchorage system, and that shows the importance of resilience. But damage percentage to the barrel increased from 2018 to 54%. Some of the typical type of damage to the barrels and most important type of damage are diamond shape buckling, and the name is because of the fact that it's similar to diamond, and elephant foot buckling, as well as catwalk indent. Catwalk indent impacted the tank significantly, and I will explain about this later. We also investigated the performance of tanks with different anchorage system, and we analyzed all the data that we had and identified that tanks with energy dissipation devices sustained less damage compared with other tanks. And that again shows the importance of having a resilience option in place. For the case of legged tank, we found out in our data that 50% of the tank sustained damage and in 2013 earthquakes, and this damage percentage increased to 57% in 2016 Kaikōura earthquake. And that makes sense because of the fact that the Kaikōura earthquakes had a larger magnitude. Again, similar figures are extracted for the legged tanks, when we can see damage percentage for tanks with different capacity ranges. Unlike flat-based tanks, we can see that the percentage of damage is increased for the case of legged tanks. We also analyzed the damage percentage to different sections of the tank, and as expected, we noted that legs or frame of the tank sustained the largest damage in both 2013 and 2016 earthquakes. Some of the typical damage to the leg are leg buckling or external or internal leg tilting, brace buckling, and global movement. The global movement means that the tanks is shifted to the other side, and that can be identified by looking at the signs that it will have on its original location. We also investigated the performance of tanks with bracing and the tanks with no bracing. So on the top of a slide, you can see an unbraced legged tank, and on the bottom there is a legged tank with bracing. And based on our data that we have of 173 tanks with bracing, 95 of them did not sustain damage, which means that only 45% sustained damage. While for the case of tanks with no bracing, 62% of them sustained damage. So that shows that the tanks with bracing basically sustained less damage compared with tanks with no bracing. And also the severity of damage to the tanks with bracing was more than that for tanks with no bracing. We also investigated the performance of the empty and full tanks. On the top of a slide, we have the figures for empty tanks, and you can see that the total percentage of damage for empty tanks was 45%, while the percentage of damage to the full tanks on the bottom of the slide was nearly twice at 85%. And that shows the importance of liquid level and how it can impact the performance of the tank. Some of the key learnings from our wine tank damage data are written in here. So basically the damage type that caused tank replacement based on our observation was ponding and overturning, and that was because of the some legged tanks that could be overturned or impact their neighboring tanks. Some parameters influencing the damage percentage was level of liquid, the capacity of the tank, and anchorage system. And also we understood that 86% of tanks with damage anchors required or at least recommended for anchor replacement. And also above 90% of tanks that having buckling such as elephant foot buckling or diamond shape buckling require different sort of repairs. And as I discussed, legged tanks perform better than unbraced legged tanks. One of the surprising and interesting thing that we noted in our data was related to the catwalk and how they can impact the wine tanks. Based on our data, we understood that 24% catwalk indent was noted for flat-based tanks. And that led us to start a new research on the seismic performance of catwalks. We have two types of catwalks, tank-supported catwalks, when the catwalk has a joint with a tank wall and tank is acting as the main frame or supporting for the catwalk. And on the right, we can see a self-supported catwalks. When the catwalk structure is sitting on its own frame, and in some cases it has bracing, and it can be designed by according to the New Zealand steel design standard. Based on our data, we understood that following the earthquake, and it might be different now, but tank-supported catwalks were more frequently used in New Zealand wine industry. And self-supported catwalks obviously performed much better with only 1% sustaining damage or 5% sustaining causing any sort of damage to either tank wall or tank con. While tank-supported catwalks perform poorly and 20% of them sustained damage and 36% of them caused damage to the wine tank. Yes, on our data, we found out that there are two main reasons for damage. One of them was because of the insufficient distance between catwalk structure and the tank. And when we identified collision between catwalk and tank structure, either con or wall. Another reason was indent on connection between tank and catwalk. Just to give you further information, the tank wall, as I said, is very thin, and imagine a 2 mm tank wall is impacted during an earthquake or moves towards the catwalk, or catwalk moves toward the tank wall, and it can cause damage to the tank wall structure or vice versa. We believe that there are two proposed solutions that needs engineering details, and to reduce the probability of damage from collision between probability of damage from collision between catwalk and tank, a sufficient distance between the tank structure and catwalk needs to be designed, and to reduce the probability of damage arising from tank catwalk connection, sliding joints can be put into place so that the tank and catwalk can move independently of each other. Based on our damage assessment, we also noted that there was a kind of indication of relation between the performance of tank anchorage system or legs with the catwalk indent for the case when the tank has a catwalk attached to it. So 33% of flat-based tanks with catwalk indent also sustained anchorage system failure. And that percentage was 92% for the case of legged tank, when the 92% of legged tanks with catwalk indent also sustained leg frame damage. We also investigated the remedial options that were recommended and followed for the flat-based tanks and legged tanks. For the case of flat-based tanks, one of the typical remedial solution was to extend the extend the skirt and add anchorage system, energy dissipation anchorage system. Another option that was followed was to remove the isolation layer to find out the buccal shell part of the tank, and then remove that buccal shell and replace it with a new section. For the case of legged tanks, we understood that there was a cases when the tank that sustained damage converted from legged tank to flat-based tank, and that was done by extending the skirt and adding anchorage system to the skirt. And one of the temporary solution for the damaged legged tank was to add a steel and weld a steel plate to the bucket legged tank, but that was a temporary solution. Based on our data and peak ground acceleration values that we could estimate, we could produce fragility curves. Just to give you a background about fragility curves, they are a tool that can provide probability of financial loss and probability of earthquake damage to structures during the future earthquakes. So we could estimate the peak ground acceleration, and based on the damage data that we had, we spent a lot of time to produce damage estates. That was particularly difficult because there were no guideline for the introduction of damage estates for the case of wine storage tanks, but we used some of the available guideline and try to match them with the reality. So we also considered again both tank types, flat-based tanks and legged tanks, and also we produce fragility curves based on different capacity and liquid level. Let's have a quick look on our damage states. We had 6 damage states, and our damage state 1 was when there was no repair required. Our damage state 2 was when no repair was required. Damage state 1 was when there was no damage. And DS2 or damage state 2 was there were no repair required, and we think that the approximate repair cost would be negligible, maybe 0 to 10% of the replacement cost. And for the case of DS3 or moderate damage, that was when approximate range of repair was between 10 to 25% of replacement cost. And for the case of damage state 4, that was when localized replacement required and approximate range of repair cost was 25 to 50% of replacement cost. For case of damage state 5, which is severe damage, is when the tank sustained significant elephant foot buckling and diamond shape buckling, and section replacement is required, and the damage can be significant, and approximate range of repair cost as a percentage of replacement cost was 50 to 75%. And complete damage was when the repair was not possible, or it was beyond repair, and approximate range of repair was between 75 to 100%. This is our fragility curves for flat base tanks. So as I said, we develop fragility curves for the empty and full tanks. So on the left of a slide, you can see the fragility curves for the empty, and on the right for the full tanks. Most of that is based on the data that we had and the peak ground acceleration that was estimated. So most of our data was between 0 to 0.5 G. And imagine if an earthquake, just to show you how it works, we have peak ground acceleration on the horizontal line, and we have probability of damage on the vertical line. So imagine if an earthquake that creates a peak ground acceleration of 1 is occurred, which is actually 2.5 times of the peak ground acceleration, the maximum peak ground acceleration that we had for wineries in our damage data. The probability of damage would be around 20% something. And when the flat base tank is empty, and when the flat base tank is full, that percentage can actually definitely goes up to about 70%. So that's a really good tool that provides opportunity to estimate the probability of damage and also some losses. We have similar data. We could develop similar fragility curves for the case of legged tanks. As you can see, probability of damage for the case of full legged tanks is more than probability of damage for the case of empty legged tanks. We did also a shaking table test. Thanks to one of the wineries and nice people there, we could bring a legged tank into the University of Auckland structural testing lab. The tank size was huge, so I just put a figure of myself to show a scale of myself in compared to the tank. And I have a height of 1.8, and the tank had a 6-meter height, so you can see how big the tank was. We develop a test program. We approximately attach 40 instruments to the tank wall and legs of a structure, and to measure acceleration, strain values, and global movement of the tank. You can see that all those cables that are attached to the tank are all going along to be attached to our data acquisition system. We consider 3 different base conditions: unanchored and laterally anchored. When the tank is only laterally anchored and it can move upward or vertically, and when the tank is fully anchored, when the tank is laterally and vertically, is completely anchored. In order to reduce hazards from possible overturning, we used an steel beam. One end of the steel beam was connected to the concrete strong wall, and the other end was connected to the tank con using strap cables. We considered 3 different testing: impulse test to identify the natural frequency of the structure, harmonic test to harmonic test is kind of artificial shaking that, and you can give different frequencies and varying shaking level to a structure. We also considered earthquake record test, and we used Christchurch and Chile earthquake. So just to give you a background about Chile earthquake, that Chile earthquake in 2010 caused substantial financial losses to the wineries in Chile, and the earth shaking table was recorded about 1G shaking, which is, as I said, 2.5 of the maximum peak ground acceleration estimate that we had for wineries in our data. Let's see some of the videos that can better explain the tests. So this is a harmonic test, frequency 2 Hz and peak ground acceleration of 0.4 G. You can see the tank is shaking on the shake table, and that is really important, particularly for the case when the tank has a catwalk, pipe, or any other structure attached to it, or either it can impact the neighboring legged tanks or flat base tanks. You can see this is a harmonic test, so the shaking is more tidy, and here is a view of one of the leg during the harmonic test to just show the how the leg can be moved during the earthquake. There is a huge noise that I'm hearing, but unfortunately I think it's not possible, so it's only me that I'm hearing that, but it's really sometimes scary. So this is the earthquake record test. I cropped some of the videos, but basically you can see that the tank is still shaking, but the type of tank shaking is different because it's an earthquake record test, and earthquake record tests are different from harmonic tests. So you can see that there is sometimes a sudden shaking, while sometimes there is no shaking. And one of the important thing is the duration of shaking, because imagine if the tank can just continue shaking on the table, it can keep impacting the other structures, or other structure can keep impacting the tank. So that shows the importance of anchorage system, and because on the next slide I will show you how anchorage system can reduce the probability of shaking and damage probability. Normally earthquake typically starts slowly, and then they will have some ups and downs, and they reduce. We have also a shaking table test for when the tank is laterally anchored, so it can move and do rocking, and when the tank is fully anchored. So let's see and compare the results. That is when 130% of Chile earthquake considered as input. So you can see that the tank starts shaking up and coming down. That collision with the shake table again creates a lot of noise. Now when the tank is fully anchored and similar earthquake record is used as input, so we can compare the results. All these cables, we had a lot of challenge to connect them in such that they don't go under the tank, particularly when the tank was unanchored. But you can see that the legs and other part of the tank are all instrumented. So you cannot see any lateral or rocking movement of the tank. One of the things that we noted when the tank was anchored, the maximum acceleration was recorded at the top of the tank, while when the tank was unanchored, the maximum acceleration was at the base of the tank. And that was interesting on our results. And also we understood that the damage, the best similarly with our damage database, percentage of strain and the level of strain on legs was more than a strain on the tank wall. And also we understood in our damage database that percentage of damage to the legs is more than other sections of the tanks. So thank you so much for attending, and thanks Landcare Research Center for providing the opportunity for me to present my research. I'm happy to take your questions.
Thanks very much, Mohsen. So there are a couple of questions. So one of the first questions was, did you collect data, or is there a difference between tanks of the same volume that might have different circumference? So if a 5, so did the taller tanks, was there a difference in terms of likelihood of damage between taller tanks and shorter squatter tanks that might have had similar volumes?
Yes, we didn't have compared that for similar volumes, but we had data for some water treatment short or broad tanks, and they did not sustain any damage similar to the wine tank. So, and that could be because of the fact that they have lower height to radius aspect ratio, because that could be a driven factor. And also the other thing could be because of the fact that those tanks typically have larger fin tank thickness, have larger thickness on their tank wall.
Right. And someone also asked kind of about the videos, because you did point out that when the tanks are full, there's sort of a 70% likelihood of damage as opposed to sort of empty tanks. And so there was just a question about whether in the video the tanks were full or whether those were empty tanks.
Yes, that's a good question. The tank was empty because of the COVID restrictions and other issues. We could not put the liquid into the tank, but that is something that we are working on so that we can use those data, we can use those data that we captured from test of empty tank, and we can model the tank using the finite element modeling software and compare the results. And when the model is refined, we can put the liquid into the tank, into our model, and get the results to ensure that our modeling will be valid.
Yeah, that's interesting, because I think the other sort of interesting thing that struck me is that, again, we saw this in the 2016 earthquake, that because there was so much wine held on site and on premises at the time of the earthquake, yeah, that presumably was a factor in the fact that there was so much damage to tanks, was that many of the tanks were full.
Yes, in actually 2016, we noted that damage percentage to the full tanks was much more than damage percentage of the damage to the empty tanks. And as I think I explained in one of the slides, it was a little bit less than twice the damage percentage compared with the damage percentage to the empty tank.
Right. And there was just another sort of slightly related question. So doesn't an anchored tank sustain damage higher up? So we showed us the video of the legged system, but due to the shaking near the top of the tank, does damage occur up there?
The damage was not really significant, so that was not really, so there was some strain values, but still the strain values on the legs was more than the tank wall, and you can see that the legs did not sustain any kind of visible damage. So that shows that the answer is no, because yes, there are more acceleration at the top of the tank, but the strain values are still more in the legs, and based on or observations, the legs are actually still doesn't show a significant damage.
And what's the significance of the thickness of tank walls? So was that part of the analysis?
Yes, that's a very good question, because we have done some preliminary analysis on tank wall thickness, which I did not present today. And we understood that tank wall thickness can particularly be important for particularly when the buckling is the matter of fact. There was, however, there was some sort of relation between anchorage system and buckling, which we did not go into the detail of analysis, but our damage data shown that when the tank did not sustain damage to the anchors, the damage to the tank barrel was less. So that could show a kind of relationship as well.
I guess, and this is kind of this is not an engineering question per se, but as you know, that there were wineries that did take the opportunity after the earthquake to either replace or retrofit tanks, replace bolting systems, and so on. And I was just wondering if you had any comment on, what are the sort of, is it a cost benefit thing, given it is quite expensive to replace tanks, and the marginal benefits would only be realized if there was a substantial earthquake? So kind of what are your reflections on either the extent to which the industry is starting to replace tanks and implement some of these solutions, or whether there's still very much a sort of, there's just some prohibitive costs involved?
Yeah, that's a very good and important note, I think. Basically, for the case of wineries and wine tanks, I think when we compare the price of wine that is in the tank and compare it with the price of the tank structure, we see that the wine is really important. So that price of wine is much more than price of the tank, at least for the larger capacity tanks. And so I think it can be really kind of important point that wineries also might be aware of, because I think each of these earthquakes gives normally lessons, and the lessons that are learned are used for the winery, and winery stakeholders use these lessons. And when we compare the, as I said, damage percentage, at least in our data for 2013 and 2016 for the flat-based tanks, shows that damage percentage reduced for the flat-based tanks in our database. And that's something that I think wineries probably are aware, and particularly the awareness might be much more than before.
Yeah, that's very, very helpful. Yeah. There's just another question. So why does the wine industry use tall, narrow tanks? And is the sort of, basically, is it a good option, or is it possible to shift to lower center of gravity tanks to reduce some of those risks?
Yes, that's a good question. I think one of the reasons could be because of the space limitation that are probably in the wineries, and another reason might be because of the fermentation process, which I'm not fully aware of. These two might be the reasons.
And so for other industries that use large tanks, so I'm thinking specifically of the dairy industry, how are these findings potentially relevant to them as well? Like, what's the sort of risk for an industry like that, which again would be located, parts of the industry would be located in seismically active areas, large tanks?
Yeah, that's a good question. We know that normally, yes, dairies have approximately similar, at least their height to radius of the tanks is approximately slender, similar with wine tanks, and these data can significantly, I think, help, and those industry also can use the data to, if needed, they can use to do some resilience measures. We didn't investigate the dairy industry, and also we could not see a significant damage data from dairy, because we did not investigate that. And we are not aware of any damage.
No, that's great. So
yeah,
I think we've answered all of Mohsen's questions, but I'm sure he'd be happy if anyone would like to follow up with anything. You can contact us, and we can make sure we connect you. Mohsen was very humble and didn't elaborate that there are a number of papers that he's published over the last couple of years based on this research in various engineering journals, which again would probably be available for you. So thank you all for taking the time out of your busy days to join us. And we really appreciate Mohsen for presenting the results of his PhD work. And as I said at the beginning, we'll be presenting another 2 webinars. The next one will be circulating news about that soon, but that will be in November, looking at workforce resilience in the wine industry. So thank you again to Tiffany for helping facilitate, and kia ora koutou.